And it's my great pleasure to introduce our very own Professor Matt Mason. I have my phone out here because Matt is extremely accomplished. Okay, and it's hard to keep everything in my brain, so I'm gonna read it out so I make sure I don't miss anything. Okay, so Matt has spent 50 years conducting research on AI and robotics, starting way back in the MIT AI lab, where he earned his BS, MS, and PhD degrees. Much of his career has been here at CMU in the Robotics Institute. In fact, he served as the director of the Robotics Institute for 10 years. From a research perspective, Matt and his research group have been studying the basic physics that govern grasping and manipulation. And they've demonstrated that these sophisticated grasping and manipulation strategies that maybe even you and I have, they can be produced by simple and robust grippers that are now used in industrial manipulation. Matt is a fellow of AAAI, AAAS, ACM, IEEE. He has lots of awards like IEEE Robotics and Automation Society Pioneer Award, Technical Field Award in Robotics and Automation. And these days, Matt is focused on logistics and on warehouse robotics at Berkshire Grey. Now, what's so exciting about having Matt here today is because he's been doing this research for 50 years, we get a really, really unique look onto the past, onto the present, and hopefully the future. And so I'm super excited to let you get into it.
Thank you very much for that very kind introduction. And thanks to all of you for being here. It's really exciting. I'm so excited to be here. There's nothing like having a daunting audience to kind of motivate, right? So I've been thinking about this, trying to figure out what I could talk to you about. And the thing that was on my mind about this is that something happened about 50 years ago. I think it's literally 49 years ago. That was so remarkable that I've been wondering about it, how on earth it happened ever since. And so I'm going to talk about that, but I was thinking, okay, I can find some other sort of twists in my career and talk about those, and we can try and distill some lessons, life lessons or career lessons out of them. Now, I'm not too sure about this distillation process, so I'm kind of hoping that you all might help out. Interrupt any time. If I say something that's stupid, please tell me. Any ideas you have, we'll amend the talk as we go, okay? And I am going to try and leave about 15 minutes at the end. So we'll see. I'll have to talk fast. Okay, but for 40 years now, I've been wondering about this amazing twist that happened, and how did it happen? Because it seems incredibly lucky. It's just too lucky to even be possible. So we're going to look at it together. Now, okay, here's all the twists. We got to think about a laser. Okay, we don't need a laser. I have a finger. So we're going to start there, 1976, how I got started in robotics, and then look at some other ones. Now, so that's the first thing, this mind-boggling twist. So what happened? As Andrea said, I was in the MIT AI lab as an undergrad, and then in 76, I got into the PhD program. But I was a generic AI guy at that point in time. I didn't know anything about robotics. I had no ambitions in robotics, no particular interest in robotics. And so I go to the orientation session in the morning, and we get our office assignments. And I go to my office, and this is what I find. Oh, gosh. Mark Rabert, Don Hollerbach, Shimon Ullman. I get the desk next to the door because, the new kid gets the crappy desk. Shimon is the most senior guy there. And I doubt that all of you know all these names, but Shimon Ullman was very successful in computer vision. Mark Rabert, probably, he was on the faculty here for a while, went to MIT, founded the Boston Dynamics. Oh, a laser. How? I'm doing. There we are. Wow. That was clever. So, Revert, and then I think I said most of it, recently founded the Robotics and AI Institute, the RAY Institute. And Judd Hollerbach, he was the editor-in-chief of the #1 journal in robotics for many years. And then Tomas Lozano Perez was in an office nearby. And some of you would know the name. All these guys were on the faculty at MIT at some point in their careers. Tomas, you might say, invented C-space or reinvented C-space. So people in applied mechanics already knew what configuration space was. But what he did was to figure out that configuration space was the foundation with which you could sort of solve motion planning. And so what happened was shortly after finding myself in that office, Tomas came back. He had been doing a visit at IBM Yorktown Heights, came back, gave us a talk on C-space, mind blown. These guys were awesome. They were having so much fun that I just had to switch, okay? Now, so that's where I became a roboticist. I didn't know anything about robotics until then. I became a roboticist. I'm gonna have fun with these guys. And you can see the thing I'm wondering about is what are the odds that those 3 or 4 people would be gathered in all in one spot, and that's where I just happened to land by pure chance. It's pretty crazy. But let's see. Okay, C-space. I would bet many of you know what it is. I'm going to not dwell on it. I'm just going to spend a little time with it. Let's see. I have a note here that if I do my left arm, yeah. So this is an arm, okay, and this is a wall. And if you wanted to plan a motion from the wall to this blue point, how would you do it? It looks pretty easy, and this is pretty easy because that's such a simple case. But the point of C-space is that, so here's the C-space, and this is, this angle, the first angle is A, and that's the horizontal axis. Sorry I've been neglecting you people. So horizontal axis. And then the axis for the second joint is the vertical axis. And so every choice of these 2 angles that puts this arm inside this obstacle corresponds to a choice that would put this point in that obstacle. So this is the C-space obstacle. Okay, and if you plan a motion in the C-space, you're planning for the motion of a point. It corresponds 1-to-1 for a motion of this more complicated mechanism, but it's much easier to think about. It's much easier to compute with. Sorry. So Tomas comes, give us a talk about this. As I said, mind blown. Great stuff. It's just the fundamentally right way to think about so many problems. It's like a global picture of the kinematics of the system. And I showed you a really, really simple system, but it can be very complex, right? 3D, complicated shapes. It's very powerful. So we used it for path planning. You can do some interesting stuff with uncertainty, and you can do something with compliant motion. So uncertainty. Imagine that you don't know exactly where that system is, which is always the case, right? Nothing's perfect. So there's some kind of uncertainty blob. Or if you wanted to, it could be a probability density function. Okay, and if you then drive the system into the wall, into this contact, it projects the uncertainty cloud down to a lower dimension. And now you've got a one-dimensional cloud. And if there was another contact, you could reduce the uncertainty to a point. Okay, it's so much better than those silly sensors. But, get rid of uncertainty using contact. So that's one thing. But then here's the thing most relevant to me. If you think about this robot moving along the wall, like let's say you wanted to draw on a chalkboard, okay? Now you want to stay in contact with it. If you don't know exactly where this is, and if you just program your arm to follow a path along a line, bad things are going to happen, right? If the blackboard is a little bit further away than you thought, you won't get any marks at all. If it's a little bit closer than you thought, you might break the chalk. even if it's exactly right, as soon as the chalk wears a little bit, so you're not going to have a line anymore, right? So you need a different approach to the control. And the idea is to put the contact frame here. When I ask people, what did I do that deserves any attention at all? They say, oh, you invented the contact frame. This was a shock to me when I first heard it, that people believe it. I don't think it's true, okay? Whatever. I asked ChatGPT the other day, and it had me in the mix with a few other people. So, for whatever that's worth. Of course, it knows who I am, so, Anyway, this is what I did for my master's thesis. I said you only want to control position in the tangent direction, and you want to control force in the normal direction. And in this case, it's very, very simple. I'm not even showing you the C-space, but it generalizes. Okay, if you use the C-space, it could be a very high-dimensional thing and very confusing, mixing translation, orientation. It's a challenge, and the C-space kind of takes care of that. So C-space is terrific, and this was my master's thesis. So I finished this in the spring of '78. If you do the math, that's about 20 months from when I got in. How did that happen? Because I really didn't know anything about robotics. Well, one, of course, is I was with this great group. So we're sharing ideas. We're exploring problems together. Everybody was very open. Okay, we had meetings weekly where we would go over a paper. We would just read one paper. We'd all read it. And then we'd get together. We'd argue about, all the different failures of it. We just shredded these papers, implicit assumptions, errors in the logic, unmotivated. We shredded these papers. And then when we shredded each other's papers as well. And so it was really a terrific group. And in that context, maybe it's a less surprising that this could happen. Still, I've been wondering about it, Is it luck I got in with that group? What's the deal? Okay, so let's do this kind of distillation of lessons process. Is it luck? Well, yeah, I was lucky, but that's not actionable, right? So I put it in parentheses. Sure, be lucky. I want to acknowledge that I was lucky. But now here's the thing, right? If I had not switched to robotics, that would have been unlucky, right? What a drag. I wanted to do real AI, general AI, whatever it is, and they put me in an office with a bunch of stupid roboticists. That would be such a drag. So, sometimes people say, never give up on your childhood dream. Well, I think actually getting up is the right thing, right? You don't want to be constrained by what some kid thought, right? Be smart. Take advantage of your experience now. And so, they were having fun. They were brilliant people. And so I said, yep, I'm a roboticist now. And so we'll put the never give up thing in the no column. We'll put be flexible there. What else do I have? Co-mentorship. I'm trying to think of the right word. It's not collaboration exactly. Like, you come into a lab and they put you on in the middle of a bunch of authors on some paper because you write a little bit of code. That's collaboration. That's great. But this was like a little bit different. It was like mentors, but it was mutual. The seniority differences were not that great. So I think of it as co-mentorship, and I've had those kind of relationships through my whole career. So these are the lessons I've drawn from it. And I don't know, you see something else I should be thinking about, jump in. Okay, well, anyway, what's next? Okay, there's another twist, which I call the intractable block. It's not that the block was intractable, but I was trying to prove something about the block, and the proof was nearly intractable. So let's see, why and when. I had finished my master's thesis. I'm trying to figure out what I'm going to do for my PhD, and I was struggling. I had no clue what I would do for a PhD. I wanted, of course, a great problem. Had to be better than that master's thesis. I didn't know I would never accomplish that, but whatever. I don't know if I said this. That master's thesis is the most cited thing I've ever done. I'm still trying to live up to what that 25-year-old kid did 49 years ago. Anyway. So anyway, I'm trying to do something interesting. And let me give you some context now. This is called the Instant Insanity demo. So this is the blocks world. Oh, by the way, that's the gold arm, so-called. That was one of the Stanford arms. And you can see it's got a simple parallel jaw gripper, and it's just grasping these cubic blocks. So the grasping is obviously kind of trivial. You will notice that it's not very precise. Okay, there's a significant error. That's supposed to be a nice tall stack. I think they probably knocked over a lot of blocks. Did you notice that after it puts the block down, the fingers do that? That's because they're checking to see if the block is still there. Okay, that's how imprecise this was. Okay, so blocks world. Everybody was doing this. It was happening at the MIT AI lab. It was happening at Stanford. The electrotechnical lab in Japan was doing it. Edinburgh University was doing it. And, you know, the grasping is kind of trivial. You parallel jaws, cubes. And this is where I had a good idea. I was looking at it and I said, I know it works. It's obvious it works, but what if you tried to prove it? Can I prove it? And I was, you know, I had been a computer scientist. I had taken a course in programming, language semantics, and formal proofs of the correctness of programs. I was thinking, okay, maybe there needs to be a robot programming language to be defined with a formal semantic. So I was thinking of some kind of proof like that. But let's see, let's break it down a little bit. So when those fingers squeeze, one of them is going to hit first. So let's say it's the one on the left there. That one's going to hit first. And now this finger is moving to the right, and the right finger is going to make contact at some point. And so in this situation, you know what's going to happen. Obviously, the block is going to move to the right along with that finger. Again, it's obvious, but can you prove it? And I could not. And then let's do the top view. So you're looking down at a block, and it's not perfectly aligned, okay? But when that finger runs into it and pushes it to the right, assuming that it does really go to the right, that alignment can be corrected, okay? So I know that's what's going to happen, and I couldn't prove it. And so that was the beginning of my PhD. And at this point, I mean, I think it's probably obvious to everybody here, but somewhere along the lines, it's like, okay, this is physics. This isn't programming semantics. This is physics. So I'll dig out my high school physics book, you know, classical mechanics. When you push something along a plane and there's friction, how does it move, okay? Pushing on a plane like this is not in the high school physics book. It's not in the freshman physics book. It's not in any physics books because it was actually not really solved. If you went back like several decades, you could find old classical mechanics books that looked at it, but they had to assume that you had that you knew how the support forces were distributed, and generally you don't. Okay, in easy sort of situations we're looking at. So how can you prove that it's going to behave that way without making any, without assuming that you know exactly how the support forces are distributed? And that's what I worked on for my PhD. Now, there's one thing left, which was nobody else was looking at this. I've never heard anybody talk about it. Does it really matter? Is it significant? These motions are really, really tiny. The graphs obviously work. Does anybody care? And then I saw this, another Stanford video.
The third segment demonstrates the mounting of a hinge.
Can you hear the audio?
Two arms. The arms cooperate, but in one of the simplest ways. That is, only one arm moves at a time. The blue arm first pushes and then centers to locate the hinge.
In that first video we saw the hand just came down surrounding the object and squeezed, right? And that's how almost all blocks world grasping happen. But in this case, it came down to the side, okay? And then pushed. That's because the guys that programmed it understood the value of this pushing motion in getting the object aligned. And they wanted to use that before they do the other grasp. Because if you squeeze something twice, now you've eliminated all the uncertainty in its pose. That's, for me, that was the proof that this does matter and I can motivate it and it's a worthy PhD topic. So that was the beginning of my work. I'm not going to show you how I proved it, but it does, it makes assumptions. It assumes a constant coefficient of friction across the support surface. It assumes you know where the center of mass is, or you can give a reasonable guess. Some assumptions, but anyway, they gave me a PhD anyway. So, now the interesting thing about these assumptions is that sometimes they correspond to necessary conditions for the success of the operation. And the best example is, if you look back at that original thing where we're looking at it sideways and a finger pushes it and obviously the object is going to move along with it, you know what? If you go back and try and prove that, you do have to make some assumptions. For instance, you have to assume that the coefficient of friction is not too high. And the coefficient of friction is high, that will fail. And instead the thing will jam and forces will build up and the controller would fault. You would have an emergency stop, or you might bend the fingers. And so there are some other conditions. You can't make contact too high or it will topple. And so actually the proof and the assumptions required to make the proof are actually telling you about behavior that people had not considered, just because it seems so trivial. So cool stuff. What's the lesson to be distilled out of that? I have some trouble with this one. Find the hidden assumptions. I think, trying to prove something is good, but it's maybe not always the right way to go about it. So find hidden assumptions. That's the best thing I could write down there. Somebody set themselves the task of figuring out what's a better lesson to learn here, okay? Okay, it's 1982. I finished my PhD. I get a job at CMU. I am wandering the halls, and I run into Allen Newell. Newell Simon Hall. Allen Newell, co-founder of the department and the co-founder of Artificial Intelligence, and a super great guy. I run into him and he says, what's next? What are you going to do now? And I don't remember. I said, blah, 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 some new project I had in mind. And he said, it takes 10 years. You have to think about something for 10 years before you can be an expert at it. Now, I wish I had asked him to elaborate. I didn't. To become an expert at something, you have to think about it for 10 years. My master's thesis, I thought about it for way less than 2 years. And all of us for our PhDs. How many of you did a 10-year-long PhD? Well, some of you are still working on it, so there's still a chance for you, right? Anyway, I certainly didn't. I didn't know what to think about it, but I never forgot it. It's very interesting. And you know what? Many years later, this became a thing that was very, very well known. It's called the 10-year rule. If you're not familiar with it, there was a book by Malcolm Gladwell called Outliers that popularized it. So it's pretty well known now. It's either 10,000 hours or 10 years. They work out to more or less the same thing. But if you trace back from Gladwell's book, Follow Citations, it all started with a 1973 study of chess by Herb Simon, as in Newell Simon Hall, as in co-founder of Artificial Intelligence. He did this study in 73, and then in 1981, Allen Newell and Paul Rosenblum did a related paper, and then a year later, it was my good timing, to run into Allen in the hall and hear this from him. So I've been pondering it for all this time, trying to figure out, I guess my case is some kind of an exception. I don't know how. How could it have happened? And then it dawned on me, actually, as I was working on this talk, the answer is quite simple, okay? Yeah, I wasn't an expert, and in academia, in research, you don't have to be an expert, okay? You don't have to be an expert to get a win. Now, if you're playing tennis, you're not going to beat Novak Djokovic after 20 months of thinking or practicing tennis. And you're not going to beat the world champion in chess after a couple of years, right? And so the 10-year rule actually has pretty solid support over a wide range of activities, but not academic research, I'm glad to say. So you're all right. What's the lesson to put in there? Well, so a lot of people would say, oh, you need to think for 10 years. But now we're going to put that in the no column. Do not think for 10 years. That would be bad advice, especially for grad students. What do we say I put instead in the yes column? I don't know. I can't figure it out. Just do it. Don't think. I don't think that's the right advice either. So, think for at least 20 months. That's a little too specific. I don't know what to say. Okay. We're back onto my journey. Okay. The next sort of relevant thing that happened was I'm at CMU. I really don't know how to be a professor. In particular, I don't know how to lead a research group. I don't know how to formulate my own career. I want a coherent set of research projects that will lead me to some vision. And I had the idea that I should look at it backwards. I'm going to ask myself, where do I want to be 10 years from now? Let's say 10 years from now, I write a book. And that book will be a coherent description of all the awesome work that I and people in the lab did. Okay, cool. Now let's see. What does that book look like? Can I go further and maybe write an outline for the book? No, I couldn't. I took a shot at it. I stuck it, in a drawer. I'd pull it out every few months or so and work on it again. The thing is, I worked on it for 10 years. So I thought I'm going to write the outline now, and then 10 years from now, I'm going to produce the book. But, and of course, if I can produce the outline, the whole idea is there will be gaps in that outline, things that I don't know how to write, and that will be what my next research project should be, right? That was the idea. Okay, start the book up outline in 82. I actually did finish the book outline in 1992 and finished the book in 2001. We got to come back to that, though, because this is more fun, and I want to talk about my second childhood, okay? So we're coming back to the book, but first, I want to talk about my second childhood. Now, here's the thing. It's 1990. So I've been here for a few years at that point, and things are going okay, but whatever. I felt like I was just too much of a computer scientist, and I wanted to be a better rounded roboticist. In particular, I wanted mechanical design skills. I thought I need some mechanical design skills. How am I going to get mechanical design skills? And over the next year or two, I would ask all of the brilliant mechanical designers that I knew, because that's one of the great things about robotics. It keeps bringing you together with these people, So when I ran into one of them at a conference, I would say, how did you get started? And guess what? None of them said, oh, I took a course my freshman year. That's not what anybody said. Let me think, who did I run into? So the guy, those two arms that we saw, the Stanford arms, the guy that designed those is Victor Scheinman. Talked to him. Ken Salisbury at Stanford. He and I published our PhD theses together. He designed the first hand that was doing things like that with its fingers. Very cool. Steve Jacobson, who designed a very cool articulated hand. And Ralph, close your ears. And Ralph Hollis. He was at that time at IBM Yorktown Heights, but he'd done some awesome mechanical design, and I asked him. And the answers I got were surprisingly consistent. It was all about what they did in their childhood. They built RC planes. Ken Salisbury built RC helicopters. Ralph, model rockets. And, I'm going to plug your book. You should go read Ralph's memoir if you want to read about the model rockets. He talks about it in there. And I don't remember what Steve Jacobson said, but something similar, something along those lines. Okay, well, gee, in a way you could say that's bad news, because my childhood is fine. What am I can't fix that. No, wrong answer. You can fix it. Relive your childhood, but debug it. And that's yet another amazing thing about robotics is that it encourages you, in my case, even requires you to relive your childhood, to go play. And so I did. I said, well, actually, the first thing was I got a bunch of construction sets and I built all the models and the manuals. And then I got myself an RC plane kit, and both it looks kind of like that. I got really good at using CA glue. Story I don't have time to tell. If you're doing this, be sure you don't squirt CA glue into your nose. Well, I didn't, but a guy did. He did not stick his finger in there. That's important. He says. And then one day I'm walking along Oakmont, not that far from here. Piece of paper comes blowing up the street, and I think, okay, I was a Boy Scout. I'm going to do my good deed for the day. I step on the paper, pick it up. I'm just going to walk up and throw it away. But I look at it, it says East Street Raceway, radio-controlled car racing every Sunday. Okay, it was a Sunday. So I walk over to the East Street Raceway in Oakmont, and this is what I saw. Here's the, this is not the East Street Raceway, but it's very similar. Now, look at these cars. These are 1/10 scale, off-road, dirt, electric. And you can see how high they're jumping. They're jumping about as high as that guy's head, okay? And that's the experience I had. When I walked in, I thought, when I was a kid, we had these slot cars, and it's like on a table, and, and the cars are about that big. And I thought I was going to go in there and look out at the track and see these little cars going, whiz, whiz, whiz. And instead, it's like, some car jumps off the track, and it was dazzling, and so I was in, right? I had to do it, and I recruited my son to drive. I was going to be the pit crew; he was going to drive, but then I had to buy 2 cars, and we both drove. Anyway, these cars are amazingly sophisticated. It's really, really crazy. This is the battery. There's an RC receiver. Oh, here's the battery. Sorry. RC receiver here. This is a differential gear. My intuition for this was somewhat lacking. I couldn't imagine you needed a differential at this scale, but you do. The craziest thing maybe is these shock absorbers, okay, you can vary the stiffness of the springs. They're color-coded. You choose different stiffness of springs depending on track conditions. The oil, even the oil in these shock absorbers, you can change the viscosity, okay? Where these elements mount on the chassis, there's many choices for how to mount them, and it just goes on and on. Okay, so anyway, I built this thing, which took me about like 3 or 4 weeks. My son and I go to the track. As soon as we get there, we break it. We ran into the wall or something. There's a piece broken. So, damn, it took me like 3 weeks to build the damn thing. And now we're just sitting at the bench in the pit area, totally dejected. There's this kid across the bench from us, Matt something. I can't remember his last name. It's like 14 years old. It's almost all teenagers that were doing this racing. And he's like, what's the matter? We're like, we broke the so-and-so, and so we're done. Maybe we can be back next week. He says, here. He strips it down, replaces the part, puts it back together in like 15 or 20 minutes, okay? And that was our first taste of, what was actually required in order to compete with these guys at that track. And then he started telling us all the things we needed to do about how to adjust the differential, how to deal with the springs and the shock absorbers, okay? You have to take out all of the hardware and replace the steel with titanium. It makes a significant difference in the weight, and you just can't compete with these guys unless you're doing all of those tricks. You have to choose different tires every time. You have to have like a whole library of tires depending on the track conditions. And then I never got good enough at it to figure out what adjustments to make. These guys I was always leaning on them to tell us how to set up the car for that week. So I had to, again, it's the mentors thing. I hesitate to call them co-mentors. They, it's like 20 or 30 years older than they were, but they were my mentors. And, here I am a big shot professor of robotics at Carnegie Mellon. And here's this 14-year-old kid that's teaching me how to move, how to drive, and how to construct and maintain a mobile machine. That's just the way it was. And that's not even the worst. I got another story, but no time. There's a kid about 8 or 10 that, yeah. Anyways, okay, did it work? I got some mechanical design skills. Certainly not the level of the wizards that I consulted at the beginning, but enough to do some stuff. This is called the mobipulator. The idea is, I don't know if you know this, but there's a kind of duality between locomotion and manipulation. And this device, the mobipulator, right, these wheels are actually being used as hands. But if they just drag the other side of the paper, now they're feet, right? And let's see, if there's a duality, then parallel parking must have a dual in manipulation. And that's what this is. It's parallel parking that piece of paper. Sorry, there. And this is real time. Okay, paper's really light, so the parallel parking, you can speed it up. And we did that once, and look at that, it came back exactly where it started. So believe me, we never did it again. Yeah, that's that. Anyway, this is another version. This is the RC mobipulator. This one is 100% hobby technology. Okay, those are Lego wheels. That is a radio-controlled airplane and a transmitter. The axle is made by gluing 2 hobby servos together. And the chassis is the battery pack. And the 2 axles are mounted to the battery pack through a very thin strip of double sticky foam core tape, which is maybe the #1 discovery I made in driving these cars. Is double sticky foam core tape is fantastic stuff. It's really awesome. Okay, lesson. Be a child. Play, okay? If you think about it, play is evolution's devious scheme to trick you into learning how your body works, learning how to operate your body, right? I mean, kids, at least before there were video games, kids thought it would be great fun to go out and throw balls to each other, throw rocks at each other, try and hit things with sticks, okay, run, jump. Why are they doing all this? Why is this fun? Is there any logic to it? Yeah, evolution made them think that this would be great fun so that they would go and practice it and get good at it. So, you know what? I mean, you could say, I'm not going to let evolution tell me what to do. By God, I'm going to sit in my basement and play video games. No, you should lean into it, right? Do what evolution is trying to trick you into doing, and go ahead and have fun. And, it's not just evolution either, right? Our culture has all kinds of toys and infrastructure to support these kind of activities. It's a great set of learning resources. So, yeah, do it. Be a child and play. Let me ask Andre a question. My timer here says 46 minutes. I'm going to leave 15.
We have a little bit of wiggle room.
What do we have right now?
So you're good. You're good. You keep.
Okay. Well, I'll just keep talking. Okay. Okay. It's when is it now? 1992. I finished the book outline. Here's the book outline. Somewhere along the way, I figured out that I could make this book do double duty. I could use it as a textbook for the class that I was teaching every year, and then that way the students actually end up helping you write the book. That's a cute trick. So that's what I did. So this is the textbook. Let's see, I brought cops. Here's the textbook, okay, and there's an outline in there that more or less what you see right there. So I figured out, it didn't dawn on me right away, but the C-space stuff, the motion planning stuff, that's all kinematics. Kinematic manipulation. The mechanics of grasping. This is about statics and quasi-statics, okay? And the stuff I did on pushing and that I did with students on related things, that's all quasi-static manipulation. And so I would just follow the usual curriculum of a physics class, kinematics, statics, and dynamics, and then squeeze in these applications to manipulation. I have an outline, and it's coherent, and there's a gap. Dynamics. I didn't know anything about dynamic manipulation. Okay. How am I going to learn about dynamic manipulation? Obviously, I should have another childhood, right? Time to iterate. Third childhood, juggling. Jugglers know a lot about dynamic manipulation. And they love to teach juggling everywhere you go. So CMU had an awesome juggling club. There's even a couple of them that went pro and are still successful professional jugglers. And the International Juggling Association was founded in Pittsburgh. And they meet here once in a while. And these festivals are great. You just walk into this big gym and there's just people juggling like crazy. And there's a lot of people that love to teach juggling. And so I'm going to demonstrate. And if anybody has control of the framing of this recording, this would be a good time to stop showing slides and start showing just me. So there's three-ball juggling. Now, it's not as hard as it looks. The main thing is, the first thing is you want to do this pattern that's kind of like a figure eight. That's the pattern, okay? If you are just trying to figure out on your own, you'll probably try and do that, which is really hard. I was quite lucky there, and it's much easier to do this. Now, the way to learn to do that, and by the way, this is called a cascade. That other thing is called a shower. So like people call this figure eight juggling versus circle juggling. If you want to learn to do that, start with one ball. The only thing really you need is to become good at accurately throwing from here to there and from there to there. So you just practice this. Just keep practicing this, okay, until you're really good at it. And when you get good at it, now you need to be able to do it even when there's a ball coming at you. Okay, so that at first, the ball's coming in at you and you panic and you throw the other ball the outside of the room. But, you get used to it. So when the ball is coming back to you, you throw this ball under it. So like this. So you just practice with two balls for a while. Always throw the white ball first, so that you get symmetric practice. Okay? And if you can do that consistently, you're actually doing the three-ball pattern with one ball missing. Okay? So now you need to just put that ball in the pattern and not panic. Okay? That's it. And then there's all kinds of huge, very simple variations. I'm sorry, I'm neglecting you guys again. Oh, wait, no, sorry, the camera's there. So you got it. Here's a very simple variation. Suppose you throw the red ball over the incoming ball instead of under, just the red ball like that. Okay? If you do that consistently, consistently, then you get this pattern, which is called either tennis or ping pong. And, the red ball is the ball going over the net. The two white balls down here are the net. So it's really simple. It's quite simple. And now the thing is, I actually didn't learn. Oh, wait. Sorry. Got to do the grand finale. I'm juggling three balls and then whoop. Grand finale. Oh. Okay, grand finale. Now, where things got interesting for me was clubs. And I did not bring free clubs because I'm out of practice. I'm sorry. I used to be able to juggle three clubs. I used to be able to juggle four balls. Never got to five balls, never got to four clubs. But this is what the club toss looks like. Now, if you're a roboticist and you're used to blocks world, you think about it and you want to figure out what's the simplest way to throw and catch clubs, you might say, if I match, the club's coming in, if I match the velocity and angular velocity of this club, the dynamics are now irrelevant, okay? Newtonian relativity, I can pretend like it's just in place and just go do a standard graph, an ordinary blocks world style graph. And to throw it, you could say the same thing. Let me get the hand moving with the angular and translational velocity that I want, and then let go. And bingo, you've got what you want. So there's a way to apply blocks world to it, and it just doesn't work. I'm pretty sure that's not the right way. If you think about what's happening, if you do this and you play with it for a while, what you realize is that your catch, the impact is important. And where you catch it, if you catch it in the right place, the impact will stop the angular velocity and the translational velocity at the same time. And that place is called the center of percussion, that they do teach in freshman physics courses. It's related to the sweet spot in a baseball bat, you know, the place where if you hit it, it doesn't sting your hands. So catching the club seems like using the center of percussion would be a good idea. We actually never used that, but never did catch things. Whoops. But the throwing motion looks like, uh-oh. Anyway, what I was saying is that you want to use Newtonian relativity and then move on to relativistic approaches. Just pretend like I was talking some very advanced stuff right there. Yeah, the throw. Really only two contact points. If you get the right motion, can you arrange to lose contact with both those points simultaneously and get a nice clean release? That's what I tried to do. And there was a guy named Michael Cass who I had seen doing this amazing stuff. Watch this. This guy could juggle with his feet. And the beauty of that is it was confirming the idea that you don't use the blocks world. You know, there's no way what he's doing with his foot there is related to a blocks world grasp. So, you know, how many contacts are there? I mean, there's an extended contact patch, but you could model it as probably 2 points of contact. And we built a thing called a pendular pedipulator and a very, very accurate acceleration of that device and then deceleration of it to get a clean release. There's exactly 2 fingers in contact with that club. And if you design it correctly, you can arrange for it to break contact with those 2 fingers simultaneously. You get a nice repeatable throw. And then Kevin Lynch was in the manipulation lab at that time. He did a PhD thesis related to this stuff and proved that, you know, a single degree of freedom arm can get control of 3 degrees of freedom of the object in certain circumstances and assumptions and all of that. Okay, lessons learned. Well, again, be a child, play. And there's something that's a little bit broader I want to mention, which is crafting your personal growth. So if you read the 10-euro rule literature, you know, it's not sufficient to practice something for 10 years. You have to do the right kind of practice. Okay, so you have to think about where you are and where you need to be and craft your activities to develop the skills that you want. And I guess I just kind of discovered that fortuitously with that book outlining process and so forth. So I think after that, you were bowed down. After that, I was the director of the RI. What happened was I finished the book and then like, oh, wait, where's my plan? It's done. So I ran off the end of my plan. So I became the director of the RI. Did you know that? And then when I stopped being the director of the RI, and Marcial started being the director of the RI, I joined Berkshire Gray to do warehouse robotics. I'm not talking about that because I talked about it here a few years ago. And just recently I started a blog, and here I'm plugging the blog, emptymason.com. And the last thing I want to say, I look at all of these lessons and I think, you know, they're all kind of conditional. Depends on the situation, whether it's going to be useful or not. Except I think there's one that's really general, that's really universal. In all of these cases, there was a community, you know, the East Street Raceway, it's a bunch of teenage kids. At MIT in grad school, it was Raybert and Hollerback and Lozana Perez. Here, a lot of the people that I'm talking to, right, the faculty here, graduate students that were in the lab, and all of the students that were in my lab, everything was, of course, a collaboration. So, and I just want to thank all those people. And TMTN, there certainly are a lot of them. And so that's it. That's it for me. And do we have time?
You do.
Okay. Yes, sure.
All right, so you've had this long career, you've done all these important things. Your philosophy has been really important along the way. A lot of us have followed in your footsteps, but it's a careful analytics, mathematics, understanding the problem at first principles. And now today we're in this world where there's these huge models and people are poking at them. And that you could argue that constitutes what robotics research is today. So I'd like to get your take on that and how we should manage this particular
Are
moment.
you sure
we're
we
in.
have time?
We have until 4 in the room.
Oh, no. That's a great question. You know, I mean, machine learning, I'll tell you, there was a point in time where I thought I could be the first person in the robotics community to work on learning robots. Actually, around 1989, Tom Mitchell showed up. I started talking to Tom Mitchell, and we cooked up this learning robots program. And that was actually what I mentioned him a second ago. Kevin Lynch was working on at first. So I'm a big fan of learning. We wanted to learn models of how the world works, and then use plain old motion planning to take advantage of that kind of a model. The idea of doing like end-to-end models certainly never crossed my mind. I did see what's his name that invented reinforcement learning give a talk. The guy was recently bragging about how successful that's been.
Rich Sutton?
Yeah, Sutton. And I thought, okay, come on, high dimensional space, that's ridiculous. That'll never work. But on the other hand, when I would think about what's going on up here, how people work, and think about all of the different behaviors that people have, and then what happens when you come and look at a new scene, and you have to somehow identify, the right behavior and be able to adapt that behavior to the new scene. And I just couldn't really conceive of how we were going to solve that problem. And I was thinking that machine learning might be a great tool for that research. Now, I wasn't thinking machine learning people should just push us out of the way and solve it, and and it's done. I was thinking the machine learning would be a good way to learn about that whole process and and guide future research. So where are we now? I don't know. I mean. A lot of the videos we see are, of course, cherry-picked. A lot of them are steered towards encouraging investors. It's hard to know really what they're doing. There was a recent paper by the TRI people that delved a little bit into sort of in a more responsible way, I would say, how you characterize and measure progress in the field. So that I thought was interesting. And so to sum all of this up, I think the answer to your question is I don't know. It's a tough one.
Yeah.
Then.
So you're talking about robotics, a very interdisciplinary field where you started at CS, but then you went to look at mechanics and stuff, but you kind of moved around. What advice would you give for an undergrad right now in CS? But what advice would you give an undergrad who wants to get into robotics, deep into it, but is right now, for example, in CS, or should someone focus on getting really good at one thing, or being very, very at a lot of different stuff?
I think you should go to the Robotics Institute web pages, look at the projects that are there, and if you see one that looks really exciting, then you go and bang on the professor, the faculty member's door, and that's how I got into AI. I didn't know what I was doing. There was the AI lab, the MIT AI lab was behind locked doors, so I would go and loiter and try and sneak in, and then I looked in the phone book and I realized this guy Jerry Sussman had 2 offices, one of which was accessible all the time. And so I went, banged on his door, told him, I wanted to do research. I didn't know what research was, but that's what I said. And that was it. And he said, okay. And then I'm working in the AI lab, and then, the rest of it, Thank you. Sure. Yeah.
Hey, man, thanks for a great talk. I'm a big fan of your blog, especially the inner robot one, the inner robot one, the vacuum gripper. So basically, the inner robot is like it's just for people who didn't like. You should read Matt's blog, by the way. You know, because like we human, we don't even understand how we like manipulate objects. And there's a secret robot in our hand, in our brain, handling all this system-wide intelligence. So the question is like, how do we tackle the challenge? How do we design a machine that can learn this inner robot or system-wide intelligence? Is this possible? And do you think we have to understand how humans do that first before we solve this on robot, or like doesn't really matter?
I would guess the people who are trying to learn from demonstration, I think they would say that's what they're doing, right? So you get a human being and you have them teleoperate a rig, and you're recording, you're getting all the data from that, and then you're using that to build a robot that does the same thing. I will say this, I think that we're all handicapped by not fully appreciating what it is that humans do. So, if you've got this, all the unconscious processes that are solving these incredibly complex sets of problems, but they're doing it so quietly, right? That's the inner robot. You don't appreciate what's going on, right? You just think, all I have to do is say pick it up and it picks it up, right? It's easy. And so you don't appreciate what's going on. Now, if you're that naive, then I think it just leaves room for prejudices. And so I think, when we were all doing the blocks world, that seemed like that was like the whole universe was manipulation. How naive were we, right? We think it's like picking up one object at a time. It's a block, very, very small subset of human manipulation behaviors. And I'm not sure when we see these robots doing teleoperated things, like in a make-believe kitchen, I'm not sure that I'm not sure how much of the gap they have closed. I think they might be still quite a bit closer to the blocks world than they are to the true repertoire of human manipulation. So I think we need to watch out for those prejudices, and I think we should have more studies of human manipulation in the wild. Just put on one of those head-mounted cameras and watch everything you do with your hands for a week, and then spend the rest of your life trying to understand it. Is that a question?
It is.
Okay.
I have a question. So I want to talk about the future. If you had to pick one thing that you're really optimistic or excited about the future of robotics, what would you say is making you excited?
Oh, that's interesting. Well, I am excited about the advances in machine learning. I'm puzzled by how we're going to integrate it with other approaches to robotics. And I'm worried about what happens if the bubble collapses, if the money decides to run somewhere else. So I am excited about it. What else? There is a lot going on. It's actually, I think probably it would be easy to come up with a list of 20 or 30 things to be excited about. To pick one of them out is a challenge. One of the things I'm excited about is the work that was recently happening in my lab. And, the Shanyi Chang, who now works at Duke, Yifan Hu, who is now doing a postdoc at Stanford and just about to be on the job market, so, And Eric Wong, who did the first efficient algorithm to enumerate all the contact modes of interacting objects in 3D. Can you believe that didn't happen until like 5 years ago? That was Eric Wong's work. So I think that should be getting a lot more attention than it does, right? People talk about dexterous manipulation, and these folks figured out some techniques to do dexterous manipulation, automatic planning of it, that I think is very cool. So close to me, but whatever. Yeah.
Sorry.
Oh yeah.
Please.
You and then And then you, what's your, yeah.
So Matt, what do you think are the gaps we need to close for actually achieve dexterous modulation? Right? Is it
Before we achieve what?
dexterous modulation? Is
Oh.
it hardware or is it more on the opposite side?
Yeah, that's a great question. Isn't this word dexterous annoying? I mean, I used it myself just a few minutes ago, but it's so annoying. Why don't we have a better word for that? Hardware, yes. Software, yes. I think the main gap is that we just don't understand what people are doing, and we're not very good at scoping it out. So, you know, one of the great things about working at Berkshire Gray is that we're working on well-defined problems, and they're driven by a real need. And so, you know, other companies are working on closely related problems, and so you've got you've got some action there that's going to result in real progress, real measurable progress. Now, when people say we're working on general purpose manipulation, what does that mean, right? Sometimes they might say we want a robot that can do everything. Well, no, you're not going to do that, right? People can't do everything either. So whether they say it or not, I think when they use that term, they might be really meaning to say we want to be able to do everything that a human can do. What can a human do? We don't know. We really don't know. Despite several studies and taxonomies of grasping behaviors and so forth, we really don't know. And so I think there needs to be a lot more work on that, and I think there's going to be like a much larger set of behaviors than anybody recognizes, and the problems of characterizing them and understanding them, I think, would be a real problem. And I think machine learning can really help us with that. Let me think. Do I see another question?
Yes.
Oh, yeah, Howie.
So in your talk, you said you not relived your childhood, but you had a new childhood. So
Yeah.
the first one was building airplanes, and the second one was the race cars, and the third was juggling. What's next?
Oh, the first one was my first childhood was all manner of things. Best not to talk about that. Second childhood was RC cars and RC planes.
Okay.
Developing some mechanical design skills. The third childhood was dynamic manipulation, juggling. Really, I did do some of these things when I was a kid, but not enough.
So what's the fourth thing gonna do?
Oh, that's a good question. I'm 73 now. If I engage in another childhood, people will just think I'm senile. I don't know. Do you have a good idea?
We can talk about them later if you want.
Okay.
Here's a question over on the left. Yeah.
Hi, Matt. In your blog, you mentioned that the vacuum grippers will not go away, and how that'll have some of its work, and then Dexter's hands would say. So the first thing when I read that, the first thing that came from my mind, can we like combine these two, and then the next thought I had was Spider-Man, like how he can just
What was that word?
Spider-Man, like how he can just,
Oh, it's Spider-Man.
yeah.
I hadn't
So I
thought
was-
of Spider-Man.
So I just think, so I just wanted to know your thoughts on, will the field kind of converge into combining these two?
Yeah, I think that's a real opportunity. And Xianyu Cheng in my lab jumped on it, did a little bit of work on it. King Goldberg at Berkeley has done some work on modeling suction grippers. I think we need to do a lot more. And that's, I think, an example of where our prejudices sort of have kept the interest in suction gripping at a minimum in the research community. But I think there are real opportunities there. Another example is an octopus. And there was some interesting work by a guy who was at Maryland and now he's at Georgia Tech. I'll think of his name in about 20 minutes. Who did some interesting work kind of inspired by an octopus. So yeah, I think combining them would be a great idea.
We have time for maybe one more.
Any burning questions?
Okay. Does anybody? Okay. Yeah,
No,
good.
go for it. No, go
Move
for it.
Doesn't anybody have another idea to add to the list? Either yeses or nos?
I think you had very few no's compared to the yeses. Is there a
That's true.
secret to that?
Well, I'm a slow learner. Garth had something.
It may be cliche, but I'd say keep your heart in the work. You always struck me as someone who was very driven by curiosity its whole way, and following this path because you wanted to. And it was not about external reward, it was about just the work was fascinating at every step.
Yeah. Keep your heart in the work. Curiosity. I will add that. That's good. Thank you very much.